Swayam Prabha. Digital India. Educated India.
Hello students, welcome to the class on pericyclic reactions. So today's topic is ENE reactions. So ENE reaction is a classic example of the group transfer reaction. In the previous class itself we have discussed about the group transfer reactions. So then what is the difference between the actual group transfer reaction and the classic example, that is the ENE reaction? Means in the case of group transfer reaction, a group or groups may migrate from or transfer from one reactant to the another reactant molecule in the same reaction in a concerted manner via cyclic transition state. Similarly, in the ENE reaction, so a hydrogen will migrate or transfer from one reactant molecule to the another reactant molecule in a concerted manner in a via a cyclic transition state. So ENE reaction can be seen in the case of an unsaturated system. Of course, all the pericyclic reactions will be seen in the case of the unsaturated molecules only, right? So what does the definition says about the ENE reaction is, it happens in an unsaturated molecule which has at least one allylic hydrogen. So the minimum requirement of ENE reaction is an unsaturated system with at least one allylic hydrogen is capable of participating in the ENE reaction. So similar to the group transfer reaction, this hydrogen has to transfer onto another system or another molecule. So the other reactant molecule should be also an unsaturated system, and the basic difference between these two is like, so the ENE, which is all the reactant molecule, one of the reactant molecule is called as ENE, which has allylic hydrogen. So other unsaturated system should be electron deficient in nature and is called as enophile in the reaction, right? So the definition of a ENE reaction is the reaction between an unsaturated system with an allylic hydrogen, which is also called as ENE, with another unsaturated system or pi system which is electron deficient in nature, which is also called as enophile under thermal conditions via a cyclic transition state in a concerted manner is called as a ENE reaction. So the product will be like this. So this is the product. So what is happening here in the end of reaction is, you could be able to see a new carbon-carbon sigma bond is formed, and also you can see the migration or transfer of the hydrogen from this ENE to enophile at the end of the reaction. So it happens via a cyclic transition state, right? So what is happening means, the sigma bond which is already with the hydrogen is slowly breaking down and then formed here. So the pi bond which is here is slowly moving here to form a sigma bond. Another pi bond here in the ENE system is moving here. So you will be able to see a 6-membered cyclic transition state. 6-membered cyclic transition state is seen. And how many electrons are involved here? Again, 6 electrons are involved in this particular reaction. So if you clearly or closely observe this reaction, you might get into your thoughts like, one of the pericyclic reaction which we have discussed in the earlier class, that is the cycloaddition, is almost similar to this one, right. So, what is that reaction? So, yes, correct, Diels-Alder reaction. In the case of Diels-Alder reaction, what you have observed is there will be a diene. In the place of ene, you will be seeing a diene molecule in the Diels-Alder reaction, and the enophile will also be there. So, what happens here is, so cyclic reorganization of electrons takes place between these two components under thermal conditions only and results in the formation of a cyclic adduct, right. So, similarly, in the ene reaction, in the place of diene, you could see an ene molecule which is having a allylic hydrogen. So, this also contributes 2 pi electrons from this double bond and 2 sigma electrons from this sigma bond, as well as the enophile again acts as a 2 pi electron component. So, here in the Diels-Alder, so this is 2 pi plus 2 pi plus 2 pi. So, therefore, mechanistically, though with principle the ene reaction should not be treated as a cycloaddition reaction, mechanistically if you observe, it acts as, it can be seen as, or it can be classified as 2 pi supra plus 2 pi supra plus 2 sigma supra cycloaddition reaction. Though it is not a complete cycloaddition reaction, mechanistically the ene reaction can be treated as a 2 pi supra, 2 sigma supra cycloaddition reaction, but it is not a cycloaddition reaction, that should be clear, right. So, it resembles the Diels-Alder reaction, but it is not also a Diels-Alder reaction, it is the ene reaction. So, it is undergoing the reaction via a cyclic transition state. This is also undergoing the reaction via a cyclic transition state in a concerted manner. Mechanistically, ene reaction can be treated as 2 pi supra plus 2 sigma supra cycloaddition reaction. So, the 2 pi electrons in the diene molecule is replaced by 2 sigma electrons. So, the 2 pi electrons in the diene is replaced by 2 sigma electrons. So, that is the difference. So, then what happens? So, generally Diels-Alder reaction is also a thermal reaction. That means you need to react the diene component as well as the dienophile component under thermal conditions to get a cyclic adduct molecule, right. So, similarly in the ene reaction also you have to react the ene component as well as the enophile component to get the final product, where you could see the shifting of or transfer of one hydrogen from the ene to enophile part, and then formation of a new carbon-carbon sigma bond. Okay. So, what it suggests means, because of the involvement of a sigma bond in the ene, the activation energy is much higher compared to that of the Diels-Alder reaction. For example, if this is the energy profile and Diels-Alder reaction is requiring this much of activation energy, so the ene reaction would have this much of activation energy. So, if all of the atoms involved in the ene component as well as the enophile component are carbon atoms only, you call this ene reaction as all carbon ene reaction. So, what you call this? All carbon ene reaction, right. So, in such cases the activation energy required for that reaction would fall around 400 to 600 degrees centigrade. See how much high temperature you need to provide because of the involvement of the sigma bond here in the case of ene molecule participating in the ene reaction, right. So, this reaction is helpful in the synthesis or in the formation of a new carbon-carbon sigma bond. So, synthetically ene reactions are highly appreciable reactions. See that ene reactions are classified into two types. One is all carbon in reactions whereas if the atoms are involved in the in reaction of either ene or enophile is other than carbon atoms, you can call it as hetero-ene reaction. So, there are two different types of ene reaction. One is the all carbon ene reaction and the other is the hetero-ene reaction. So, if this is the ene molecule and this is the enophile. So, this is the ene molecule and this is the enophile, right. So, if X double bond Y is simply C double bond C or C triple bond C. So, they fall under the category. So, if this is the case, they fall under the category all carbon ene reactions, right. If X double bond Y is either a carbonyl group C double bond O, where one of the carbon atom is replaced by oxygen here, or if it is a sulfur C double bond S, or if it is nitrogen, if it is a molecular oxygen, or if it is nitrogen azo group, NO group. So, any of them are representing the X double bond Y portion of this ene reaction. So, they should be called as, this particular reaction should be called as hetero-ene reaction, right. So, if X double bond Y is simply an double bond, carbon-carbon double bond or carbon-carbon triple bond, then it should be treated as, classified as all carbon ene reaction. If X double bond Y is one of these, C double bond O or C double bond S or C double bond N, OO or NN or NO, so then it should be classified as hetero-ene reaction. So, in the case of Diels-Alder reaction, according to the frontier molecular orbital theory, in order to analyze the reaction, what we have seen is you have to choose the homomolecular orbital from one component and the lumomolecular orbital from the other component, right. Similar is the case with the ene reactions. So, here as well, under thermal conditions, to drive the reaction forward, so we have to analyze the reaction. So, you have to choose the homomolecular orbital from one component, let it be ene component, and then we can choose the lumomolecular orbital from the enophile component, okay. So, always the reaction is between the homo and the lumo, right. So, under thermal conditions, the homo should be selected from the ground state as well as the lumo should be selected from the ground state only. So, the energy gap between the homomolecular orbital and the lumomolecular orbital will decide the requirement of the activation energy. If they are far away from each other, that means the energy gap between the homomolecular orbital and the lumomolecular orbital is too high, then you might need more activation energy. If somehow the lumomolecular orbital and the homomolecular orbital coming closer to each other, that means the distance between them, the difference of energy between them is decreasing. So, then the reaction would happen with a low activation energy itself, right. So, for that what we need to do is, first we need to identify the homomolecular orbital from the ene component and then lumomolecular orbital from the enophile component. So, this is the lumo from the enophile. So, this is the LUMO from the enophile. This is the HOMO from the ene component, right. So, HOMO from the ene is selected, which has the allylic hydrogen. So, this is the allylic hydrogen carbon bond, right. So, this hydrogen has to migrate or transfer to the enophile component, as well as a sigma bond should be formed, carbon-carbon sigma bond should be formed between the ene and the enophile. So, that happens here with these lobes, and then the migration happens here, a transfer happens here. So, as a result of which you will be able to see the transfer of hydrogen. Two things are possible in the case of ene reaction, that is the transfer of hydrogen, and the second thing is formation of a new carbon-carbon sigma bond. So, these two things are being observed in the case of ene reaction. So, if this is the energy profile, right, and in that, if this is the energy of the HOMO and this is the energy of the LUMO molecular orbital. So, the reaction should happen from HOMO to LUMO. So, LUMO is selected from the enophile and HOMO should be selected from the ene. As discussed in an all carbon ene reaction, the required temperatures will fall in between 400 to 600 degrees centigrade, right. So, which is huge amount of energy. So, how to decrease this energy? So, we have an option, and we have to seek some help from a catalyst. So, catalyst is the one which does not directly involve in the reaction most of the times, but it will alter the rate of the reaction. If it is a positive catalyst, of course, it will decrease the activation energy and therefore increases the rate of reaction. If it is a negative catalyst, which is also called as a retardant, so will increase the activation energy and therefore decreases the rate of reaction. So, we do need such a catalyst which can decrease the activation energy and increase the rate of reaction here. So, the best suitable catalysts are Lewis acid catalysts. So, what we can use here is Lewis acid catalyst. So, what happens with the Lewis acid catalyst means, for example, ZnBr2 is one such catalyst, which you can see in one of the examples we will be discussing laterwards. So, what the Lewis acid catalyst is capable of doing means, it decreases the energy of the LUMO molecular orbital. So, what is happening here? It stabilizes the LUMO molecular orbital. This is the HOMO, of course, from the ene component, and when you have the Lewis acid catalyst, the energy of the LUMO decreases. So, it falls around this. So, this is from the enophile, right. So, what has happened now? This is the LUMO and this is the HOMO. Without Lewis acid catalyst, what you could see here is it requires a huge amount of energy, and whereas in the presence of a Lewis acid catalyst, the energy of the LUMO has drastically decreased, and therefore, the reaction becomes feasible at lower temperatures compared to this one. Okay. So, at the same time, the selectivity of the reaction is also increased appreciably in the presence of the Lewis acid catalyst. These ene reactions will have high degrees of negative entropies. In the case of intermolecular ene reactions, the entropy will be minus 30 calories per mole also. So, ene reactions are also capable of having high negative entropy. So, they are also able to show high negative entropy of activation. So, therefore, in the case of an intermolecular in reaction, so the entropy of activation might be around 30 calories mole per kelvins. Okay. So, this is the case. So, ENE reactions are further classified into two more types. One is the intermolecular ENE reaction and the other is the intramolecular ENE reaction. So, you can see two different types of ENE reactions. One is intermolecular and the other is intramolecular. We will try to see or explain both the types of ENE reactions, that is inter as well as the intramolecular reactions, with some examples. So, look at this example where this is the pinene molecule, a beta pinene molecule. So, this on reaction with acroyl chloride under thermal conditions will undergo the ENE reaction, resulting in the formation of a product where you could see both. So, the transfer of this hydrogen as well as the formation of a new carbon-carbon sigma bond. So, where the carbon-carbon sigma bond is forming is what you need to identify first. So, this is the allylic hydrogen which is intended to migrate from this molecule to this molecule, and what is the, this is the enophile. Okay. So, it has a group which has a capacity of electron withdrawing nature. One thing, if we try to recollect, in the case of Diels-Alder reaction also, the diene molecule, if has the electron releasing groups, will become highly reactive in nature, and the dienophile component, if has an electron withdrawing substituent or group, so it becomes highly reactive in nature. Similarly, in the case of ENE reaction, if there are electron withdrawing groups on the enophile, so then the reactivity also increases for the particular reaction. So, this has an electron withdrawing group, therefore, the reactivity of this particular enophile is more. Okay. So, this is the hydrogen which is trying to migrate. Okay. So, what is happening here? You could see with the example. So, this double bond is trying to take the hydrogen, this sigma bond is moving here and converting into a pi bond. One of these pi bond is moving here to this carbon atom and forming a carbon-carbon sigma bond, right. So, the hydrogen has moved to this carbon atom. So, this is the carbon atom, and then this one CC sigma bond formed and a pi bond is formed. So, therefore, this is the product of this particular example, which comes under intermolecular ENE reaction. Similarly, in the place of acroyl chloride, if for the same ENE component, this is this, if we are using this enophile, so what is going to happen again? The hydrogen will be taken there, transferring there, and then this pi bond is going to form a sigma bond here. So, this is again an ENE reaction under thermal condition. So, you will be able to see a double bond here, new double bond, and then right. So, hydrogen has moved to this particular enophile component here and a new sigma bond is formed here. So, this will be the product. So, this is the ene component. If it is treated with a enophile like this, what should happen here? So, the sigma bond should move here and you will get a new sigma bond under thermal conditions. This is an ene reaction and therefore, the reaction should be like a new sigma bond has formed here. This is the double bond, one more double bond will be seen here and then this is the COOCH3 and CH3. So, hydrogen is transferred over here. So, this example will give you a clear cut message like, so in reaction where the hydrogen transfer and the sigma bond formation is happening in a syn fashion, syn manner. So, that is why you can see both these groups in the cis form, right. So, always in reaction will happen in a concerted manner with cyclic transition state and also in syn manner. So, this thing you should be always remembering. So, all the ene reactions will proceed in a syn manner. So, that is the transfer of hydrogen as well as the formation of the new sigma bond will happen in the same phase. Okay. Whatever the groups attached to the enophile will be after the reaction will be seen in the same phase. This ene component on reaction with an enophile like this will undergo a thermal ene reaction, right. So, this is forming a sigma bond and this is taking the hydrogen and this sigma bond hydrogen allylic hydrogen sigma bond is converted into a pi bond, as a result of which you will be able to see this one, right. So, one double bond has come here and this one and then this is the new sigma bond. A hydrogen is formed here, right. So, for clarity I am erasing this. So, this is the reaction which you could see here. So, what happens, what is the beauty of this reaction is, if you take one more mole of this reactant enophile, so it definitely continues the reaction and this reaction is well known to you. What is this reaction? Exactly, this is the Diels-Alder reaction, that is 4 pi plus 2 pi. Diels-Alder reaction. So, Diels-Alder reaction is nothing but cycloaddition, right. So, ene reaction followed by Diels-Alder can be seen here. So, this is going to happen, two new sigma bonds are formed here, this one and this one, right. And then, so already we have this one, okay. So, that is the final product of this reaction. So far we have seen only the all carbon ene reactions, and let us try with hetero-ene reaction now. So what do you mean by hetero-ene reaction? If the X double bond Y component, that is the enophile component, is having one or two hetero atoms which can directly involve in the ene reaction, therefore it is called as the hetero-ene reaction. Okay. So the best enophile components in terms of hetero-ene reaction is either a carbonyl group or a thionyl group or azo group or C double bond N imide group and NO group, etc. So we will see now some of the carbonyl ene reactions. So what is going to happen here? So you can see this going here and it coming here. So this is the product you will be seeing in the carbonyl ene reaction. So look at this another example where the pinene is involved here. So this is the hydrogen and this is the carbonyl compound, right. So it may be any group or hydrogen. So what is happening? So this is capturing the hydrogen and this double bond is formed here because of the conversion of the allylic sigma bond into this one, and then you will see the formation of a new sigma bond here. So as a result of which these are all same and this is the carbon and you have OH coming here. So this is one more example for the carbonyl ene reaction. So now let us go quickly into the intermolecular ene reactions. So compared to the intermolecular ene reactions, intramolecular ene reactions require low activation energy. Okay. And depending upon the connection, because in the intermolecular you need a separate ene component as well as a separate enophile component, whereas in the case of intramolecular, both the ene component as well as the enophile component is a part of the single molecule. Okay. There should be a connectivity between the ene as well as the enophile. So whatever the carbon chain connecting the ene and the enophile is treated as or is called as a tether part. Tether. Okay. So depending upon the connection of the tether to the ene component, so intramolecular ene reactions are classified into three types. That is type 1, type 2 and type 3. Okay. So we will just quickly see into the type 1, type 2 and type 3 of the intramolecular ene reactions, which has less activation energy required for driving the reaction compared to the intermolecular ene reaction. So if this is the X double bond Y, which is nothing but the enophile component, this is the enophile component and this is the ene component, right. So if the enophile is directly connected to the ene component like this, we take it as type 1 ene reaction. What is this? Intramolecular ene reaction. Okay. So this is a type 1 intramolecular ene reaction. So where the product will be like this. So what is going to happen? So this is coming here, this is going here and one more. new bond will be formed. X double bond Y is now H. This double bond has moved already and this is the thing. So, there is a connection here. Okay. So, this is the product you will be seeing. Second type is, this is X double bond Y and then this is the ene component as well as this is the enophile component, right. If they are connected to each other via this tether, so this portion which is connecting the ene and enophile is called as the tether part. Okay. So, this is the connectivity. It is type 2 of course in reaction, and what is going to happen again? The same story. Okay. So, the product is XY, Y has taken the hydrogen. So, transfer of hydrogen has happened already, and now, so this is the double bond. So, the connection is here. So, the tether part is connected to this carbon atom. So, this is type 2 intramolecular ene reaction. So, the third part is you look at this, X double bond Y is the enophile component, right. So, this is the ene component and here is the hydrogen. So, if the connectivity is here, so this is treated as type 3 in intramolecular ene reaction. And where is the bond forming now? Yeah. So, this new sigma bond, carbon-carbon sigma bond is forming between this carbon and Y, and then this is taking up the hydrogen and this is moving here. Okay. So, the product is X, Y, it is now connected to the carbon atom, right. So, this carbon atom is now having a double bond here, a new double bond, and X is having a hydrogen as well as the connectivity like this. So, this is the type 3 intramolecular ene reaction. So, look at this molecule, you could see both the ene component, so and the enophile and ene component. This is the ene component, right. So, double bond with an allylic hydrogen bond, and this is the enophile, this is the enophile component with a heteroatom. So, therefore, the entire reaction is a hetero-ene reaction and also it is a intramolecular ene reaction. Okay. What is going to happen here? So, this is abstracting the hydrogen, transfer of hydrogen is taking place and then a new sigma bond is formed here. So, you need definitely temperature because ene reactions are thermal reactions. So, how much do you need is only 180 degrees centigrade, which is much lower compared to the all carbon ene reaction as well as the intermolecular ene reaction. So, this is there, this is the new sigma bond formed between the ene and enophile, and then you will see the OH formed and then this one. So, this is the product of this intramolecular ene reaction, which is also a hetero-ene reaction. So, what is going to happen in this example? So, you see, so this is the enophile component, right, and this is the ene component. Okay. So, therefore, what is going to happen means the enophile is taking away this hydrogen transfer is being happening here. This sigma bond is converted into double bond, and then this one is going to form a new sigma bond with this carbon atom, right, like this. As a result of which we can see this product. Hydrogen is formed, this double bond is unaffected, and then one more double bond is being formed, right, here. So, with this we have completed successfully the IN reactions part also. So, we will see the chelotropic reactions in the next class. Okay, thank you.